and gentlemen, I'm pleased to welcome you here at the Group Exhibit Hydrogen Fuel Cells and Batteries in Hanover 2014. You're here at the Technical Forum, and every half an hour here very interesting and informative presentation will take place. So please come in, have a seat, have a drink on the house and enjoy with me our next presentation dealing with the topic high temperature PEM based reformed methanol fuel cells. And your presenter is the CEO from Sir Energy, is Anders Kousgaard. Come on and give him a big hand, please.
So, thank you all for being here. Welcome. I can see we skipped the first slide, but that wasn't that important. So we go straight to the first points here. Our business setup is a little bit mixed. We have the Serenity DK, the Danish company. We are doing all the research development, business development, marketing, and so on, prototype and pilot sales production. And then we have a partner, German partner, coming out of Aachen in southern Germany. Who is sort of our manufacturing partner for all the components for the fuel cell and the reformer and so on, metallic machining and so on. They also help us in terms of input to reducing costs and all the other important things about scaling up production here. So let's see if, yeah. We offer basically two types of stacks. One is the air-cooled stacks, the one in the right here, which was our first stack as well. It was developed back in 2006 and 2007 and has been, in operation ever since. About 3 years ago, we started our development of the liquid-cooled generation, which is an active area of 165 square centimeters, 120 cells. The ambition here is stack about 5 kV net gross output in the system, or net output in the system. So meaning that it gives up to about 670 kilowatt, depending on if it's reformat or if it's hydrogen or whatever it is. So what we do, the stacks you saw just before, we supply them to other system integrators who make a variety of systems based on hydrogen, diesel, gasoline, JP8, LPG, and so forth. Internally, we also have a system solution that's a methanol modules. That's the only thing we do inside, and the rest we do partnering up with different companies around. So the main market applications for these methanol fuel cell modules is basically essentially runtime extension of battery packs. That could be either lead acid battery or lithium-ion battery packs. Telecom and backup is definitely something we are focusing on with our 19-inch rack modules. Also supplemental power and even continuous power generation, where we compete about with life cycle cost of a conventional diesel generators. Besides that, we have various activities within range extension of electric vehicles, that being everything from professional vehicles, forklifts and so on, all the way to more like a project level on passenger cars. I'll come back to that a little bit later, and the big vision about using methanol in that context. So the reformed methanol fuel cells we produce is in the range from 350 watt. It's in the far left side here, the black one. That has been marketed since late 2009, I believe. We have quite a few systems. I believe about 50 or 60 systems in the operation at the moment of those. On the middle screen, that's the H3700, so that's basically just a dual 350 setup to support sort of a little bit higher level power. But otherwise, we are working a lot now on our liquid cool platform, which then covers all the way from 1.5 kilowatt over 2.5 to 5 kilowatt. So in general, just a brief slide on the high temperature PEM technology. We are at an operation temperature, when we say high temperature, of 160 degrees C. Startup times on the stack, we did demonstrate down to 5 minutes, but that requires a lot of energy to start it up that fast. So usually we see systems in the vicinity of 30 to 40 minutes in real life startup time. We do both offer the opportunity to preheat on the methanol module side electrically and by fuel. Ambient temperatures, of course, we don't see a lot of limitations there in terms of cooling, so our limitations are mainly on the choice of components we have, what kind of electronics, and in particular the power electronics we stand. So we don't have any need for water. We get regeneration or humidification of the fuel cell. We don't need to have a large parasitic loss in that context to drive up water droplets of the stack. And that means that we can make a very, very low parasitic power consumption for the air supply. Basically, we're in the 200 watts to 10 kilowatt range here. 5,000 hours, actually more like 7,500 hours, an updated number here. But on the stack level, but our ambition is to go out with a warranty, in most cases about 5,000 hours, depending on how many start-stops is in the application. So basically, this is the Alucore. So you can also come and visit it, see it on our booth just behind the scene. It's basically consisting of the. Let's see if I get this pointer to work here. Nope. Yeah, here we go. So a little bit weak. So here's the fuel cell itself, the high temperature PEM, 120 cells. We have the evaporator on this end and the reformer here. So basically, the methanol comes in here. It's being evaporated by the use of the heat produced by the fuel cell. So we are taking advantage here of the high operating temperature of the fuel cell to actually evaporate the water and the methanol. This can also be done with other systems, such as for natural gas. You also need quite a lot of water. So you take that thermal energy requirement off the reformer and basically let the fuel cell do that job. That gives you quite a few efficiency points, and that's the whole trick about why high temperature PEM in this regard is much more efficient than any low temperature PEM technology in this way. So basically, after evaporating, we pass through the reformer being converted to hydrogen. We come out with about 1% of CO, maybe a little bit less. Pass through the fuel cell where 80 to 85% of the fuel is converted into electricity, and the remaining part here is then converted into thermal energy in the burner to drive the reformer. So that's a totally integrated system. We don't need any pipes here, only this small one down here. This is what really makes the power simplicity, which we so proudly believe we are building. Besides this, of course, we need a small circulation pump here in the bottom for the liquid cooling circuit, a radiator or heat exchanger, depending on whether you're going to utilize the waste heat or just want to vent it off. So when it then comes into the module, it looks like this. It's about 6 units high. It means 266 millimeters high, 700 millimeters deep, and 19-inch rack wide. So that's about 435 millimeters. We output about 4 to 5 kilowatt of thermal energy. Total efficiency above 85% if you consider also the heat, the CHP function. Electrical efficiency, I have a graph here afterwards, but it's in the vicinity from 40 to 50%. DC-DC integrated, so we offer output voltages here from 48 volts over 300 to 450, and even up to 800 volt DC output voltage here. So it's quite flexible here on the outlet side. So here's the efficiency and fuel consumption curves, and this is really the important part. We are lying at full power at about a little bit more than 40% efficiency, and up to 47% in the low power region here. On the fuel consumption side, we are about from 0.8 to 0.9 approximately liter per kilowatt hour, and this is not methanol, this is water methanol mix. So this would correspond to about 0.5 liter per kilowatt hour of actual methanol, and the rest is water. So this is, I believe, is one of the highest efficiencies on this kind of liquid fuel system I've seen, at least so far in the world. It's quite compact, and yeah. So basically, this is how we often operate then. So we have the H3 5000 unit here, the fuel cell. We need to have a fuel tank with water methanol. We need to have a radiator, or the radiator is built in, but we have an option of having external cooling with liquid glycol or whatever. On the other side here, we have the batteries. 48, 350, 40. You have the AUX in-out, so you have some dry contacts, CAN interface, USB for software upload, and UDP LAN connection for driving GOEs for development purposes and so on. So this is examples on how we distribute the methanol. It's a IMCA industrial grade methanol we use. We pass it through a filter. Some occasions where we need to have very long operating time. 40% water is added here. Yeah. So basically we have a quick connector system here, which is non-spill, both on the module side and on the hose side, so you don't come in contact with the water methanol mixture here. So here's one of some examples of what we did on the industrial side. This is a telco deployment in the US. It was a 700 watt installation, a wall mount solution we made here with 20 liter dunks here, plastic canisters, HDPE on the bottom. We gave 72 hours of autonomy in a very, very compact space. Another one example is the material handling. A truck here, we installed just one 350 unit with a methanol tank, basically dropping in together with the battery to replace the existing lead acid battery pack. This trial is ongoing now at our partner in Germany, Fischer. Another thing we're working on is these a little bit bigger installations. These are more on project level at the moment. We are, amongst other, participating in this Paxel project, where we're installing up to 16 of these H3 5000s in each rack. That will give you a 90 kilowatt output. But usually this is used intended for high efficiency, long-term operation, so we derate it to 60 kilowatt. So this is basically 3.75 kilowatt per module. We have a 350 to 400 volt DC output, and then we connect it directly to a solar inverter. So it's three-phase 400 volt AC output. So the liquid cooling output from the fuel cells can also be used to drive absorption heating process, which makes sort of a quad generation. So first you have electricity, you have heat, you have cooling, and after that you even have desalination. This is what we're working on in the Paxel project, to really combine all these things in one. So electricity, heat, cooling, and freshwater generation on board the ship. I think it's quite some. And this is all the advantage you get from the high operating temperature and the high grade heat. So the serenity difference, we believe, is highly integrated systems. It's our philosophy. Let's skip the pipes. Let's get everything packed down into a nicely packaged box. Very high electrical efficiency, very low thermal losses. Similar system design and installation. Low maintenance. There's really only the air filter which needs to be replaced usually every 5,000 hours, and in some cases the fuel filter. High modularity, kilowatt rating can be adjusted. Currently we offer 3 standard sizes. That's 1.5 kilowatt, 2.5 kilowatt, and 5 kilowatt on the methanol side. Yeah, fuel logistics handling cost and siting, compared to hydrogen systems, of course, our transportation cost for getting the fuel out there is much lower. The runtime we obtain per liter of fuel is very long. We're talking about an hourly consumption, a full load of about 4 liter per hour of a 5 kilowatt unit. So a 100 liter container will give you 1 day's operation. It's quite good. So then the low footprint, extremely compact, you can go into 19-inch rack. So it makes it a fast installation into existing solutions. So a little switch in the topic here. We use methanol, and we'd like to also tell a little bit why we do so, and a little bit more about the bigger picture of using methanol. So methanol can be produced from a wide range of fossil and renewable fuels. Thereby, our dependency on politically unstable regions could be reduced, and national energy security be increased. You can easily store methanol for extended periods of time. In Europe today, we store, I believe it's 3 months worth of consumption to mitigate risk in terms of natural catastrophes, wars, and so on. This would also be possible with this new energy carrier. We can do long-term storage of fluctuating renewable energy by the usual hydrogen philosophy, converting hydrogen into the liquid fuel afterwards. I'll give you an example on that afterwards. And it's also a renewable option for the battery electric vehicle that basically give it the normal operating range of a passenger vehicle combined with a heat source we, at least in the northern part of Europe, need for the electric vehicles. So this is basically the different sorts of fuels, that energy sources that can be used to produce methanol. We have everything from the wind and sun through electrolysis process, gasification, biomass, waste, and so on, can also be used to produce methanol. Captured CO2 from power plants, and natural gas, of course, can also be used. This is the primary source today of methanol. It's definitely natural gas by far. But also on the consumption side, it's not only hydrogen but PEM fuel cells that use methanol. Internal combustion engines definitely already use it in China in large scale. Fuel cell systems, high temperature PEM, SOFC, and the direct methanol also use it. We use it about 60% of the world consumption of methanol consumption today goes into polymer production, and even producing higher alcohols and synthetic fuels. This is one of the example here where we combine the windmill production, with direct charging in a vehicle. I took the Audi here by purpose because we have a project with Fraunhofer Institute and other partners, including Audi, is giving input here to this project about the range extender solution from Serenity with a battery electric vehicle, combining those two things. But the principle here is that basically the excess electricity can be used to produce hydrogen combined with gasification of renewables to produce methanol under synthesis. So there are some reports done recently in Denmark on how the different CO2 emissions per driven kilometer was developing. This was a report from 2013 from the Danish Ministry of Energy. And there's of course a lot of things here, including conventional gasoline and so on. Excuse the Danish, but the report wasn't Danish. But also methanol from biomass and hydrogen. That's basically the two important here, and the electric vehicles. So for sure, it's the most efficient is to charge the vehicles directly from the grid. But actually, when we look at the efficiency of methanol and hydrogen, they're almost the same. So that's well to real. And also the CO2 emissions are very low, both of them. So if you look at the numbers, which were a little bit difficult to reach here, the 2020 renewable model CO2 well-to-wheel emission for electrical were 4 grams per kilometer in this calculation. Hydrogen was 9 and methanol was 7 grams. Well-to-wheel system efficiencies of electrical 70%, 72 for hydrogen, and 27.8% for methanol. So this shows that there's some good works on this, and that there's a good pathway forward in terms of having not only one solution but maybe 2 or 3 in terms of both hydrogen as a carrier itself, electrical, and methanol. The use of methanol today, there's about 100 fueling stations built up in '97, but today there's 20,000 flexi-fuel vehicles that are mandated to also be able to run on methanol. So this is the open fuel standards, gasoline, diesel, mixed methanol. Also, there's a lot of work now on shale gas to liquids. Some bigger plants are now being constructed in the US for shale gas exports through liquid methanol. So in China, these M85 standards has been implemented. M100 has been in operation since 2009. And actually today already covers 7 to 8% of the gasoline consumption in China. So there's already considerable amounts of methanol being used. And to Europe, there's 3% of the methanol today can be blended into gasoline. So this is the increase we see here from 2005. There's a green part of the curve. Here's the methanol for energy purposes. And this is the blue one is the industrial consumption. We really see the growth. It's actually the energy demand, or the demand for methanol for energy production. if you look at these slides, I borrowed these from Methanex. There's both 100% methanol that's being used and also the DME. So in total, there's already significant world production of methanol. Annual gasoline consumption is equivalent about 880 metric tons. Annual methanol consumption is about 70, so we're looking at close to 10% of the annual gasoline consumption in methanol equivalent. So it's actually a fuel that's already there. It's ready to use. And just go ahead. And some people then already do, with about 30 metric tons here of consumption for energy. So a few examples on what we have of activities here. Of course, this is not in the commercial scale yet, so these are project level. One of the projects we have is the McSee project in Denmark with a small Danish electric vehicle manufacturer, where we integrate a methanol range extender on one side with a methanol tank, giving it up to 800 kilometers range. And then lithium-ion batteries on the other side. We also have the green methanol project with a collaboration between OK Gasoline, which is the largest gasoline distributor in Denmark, Hamag, which is a producer of these filling stations, and Serenity for a coordination role. And this project aims to demonstrate a safe and reliable and cost-effective way of distributing methanol. So the end of the game is to have about 2 to 3 filling stations with this concept, and hopefully a small fleet of cars as well to use it. We have another project that I mentioned earlier with the Fraunhofer Institute. Fraunhofer is the project manager, and then there's a lot of different industrial partners in the project. It would be a long list. Audi is providing input in terms of the chassis construction and so on. Basically what the concept here is, you can see this actual box there. It's on the Baden-Württemberg exhibition, just a few blocks up here. This box goes in instead of the spare wheel, so we actually made a cut out here, put the range extender in, and then you actually see here on the mirror, there's a methanol tank, it's looking up, together with the lithium-ion battery string here underneath the vehicle. So this is a concept vehicle with a vision for 2030, that I think quite good illustrates what the potentials are on a bit longer horizon. So, thanks a lot for your attention, and if you have some questions, please pass them forward.
And we thank you for this very interesting, informative presentation here. So are here any question right now in the audience? So it's your chance right now. Just raise your hand, I'm coming to you, pick you up with the microphone. So not yet, but I'm not so sorry about, because we are a little just in time.
Yeah.
So yeah, if
good fit.
Yeah, fine.
But if you have some questions, please be on the other side of this wall here, and please feel free to come.
Yeah, thank you very much. So there's a short break now, and after it we will continue our program with 4 presentations about very interesting projects of fuel cells and hydrogen joint undertaking. So please stay, and thank you very much for your kind attention.